So, first of all, I want to give this to people who've never seen you, haven't heard of your work, and I think they should have heard of your work.
Yeah.
So, to start off with, what are your credentials? Who are you? What do you do?
Okay. I'm Jerry Pollack. I'm a professor at the University of Washington, and I've been doing science my whole career. And I started doing research on muscles. I did research on muscles for 30 years, and then got interested in water. And I've been studying water during the past, you might say 15 or 20 years.
So why water? What got you interested in water? I mean, why is that your field of expertise?
Well, I came onto it for a few reasons. The people who are studying the mechanism of contraction in muscles ignore the fact that 2/3 of the muscle is water by volume. And if you actually think of the fraction of molecules, if you line up all the molecules in muscles and do a count, more than 99% of the molecules are water molecules. How could it be that muscle can work and you can ignore more than 99% of the molecules? So that interested me.
That doesn't make much sense to me, just from a kind of logical perspective. If we're 99% water, why don't we just fall to pieces? How are bones 99% water? How are muscles 99% water? That doesn't, I don't get it.
Well, to fill the 2/3 volume, we know that we're 2/3, by volume we're 2/3 water, but the water molecule is so tiny that in order to fill that 2/3, you need an awful lot of water molecules. So if you do the count, it's simply that you count more than 99 out of every 100 molecules inside your muscle or inside your brain or inside your heart are water molecules. There's a framework that holds these molecules together. Some people think of the proteins inside the muscle, for example, as the framework that holds the water together. But we think a bit differently. The framework might be the water that actually holds the muscle together, because the water molecules stick together. So this comes to what we discovered in easy water, and I can talk about it now. So we discovered that there's a different kind of water. Most people think that all the water inside the body is H2O, just like this stuff, but actually it's not. We found a different phase of water. It's a fourth phase of water that has completely different characteristics from ordinary water. It's more viscous. The molecules are aligned, unlike this kind of water where the molecules are randomly disposed. And it's almost a gel-like or highly viscous kind of water. And so as a gel-like entity, that can actually be what holds it all together, so it doesn't fall apart, as you just asked.
Well, you wrote a book called The Fourth Phase of Water, right? So, okay, this is an unfamiliar concept to a lot of people. We know we have solid, liquid, and gas, and that's how water forms. This fourth phase, why doesn't anyone know about this? Why is it so unfamiliar, and why is it important?
Many people don't know about it, partly, I think, because our book was just published a couple of years ago, and so it takes a while for this material to get out. A lot of people do know about it, but it's slow to spread, as many things are slow to spread in the scientific community. There's a kind of resistance to findings that are revolutionary or new. The resistance comes in part from the scientists, because scientists often feel threatened by new discoveries. So, for example, if I'm a scientist who's the world's expert on the shape of the Earth, and all of my colleagues and I think the Earth is basically flat, and someone comes around and says, "Well, we have evidence that the Earth is round." So the usual response to something like that is keep a distance from it, because it feels threatening. It feels threatening in several ways. It feels threatening because it disturbs our equilibrium. We're very happy with the flat Earth idea. Don't disturb us with a round Earth idea. And also, it jeopardizes our careers, scientific careers, because we make a name for ourselves. We make names for ourselves in the scientific community as being, for example, one of the world's experts on the exact shape of the flat Earth. If someone comes around and they really have evidence that the Earth is round, this is really disturbing for us because it jeopardizes our standing in the scientific community. So scientists, most people envision scientists as open-minded and searching for truth, and to some extent, of course, that's true. But to another extent, it's actually not as true as we would hope. We tend to cling to our belief systems. When someone comes around and challenges our belief systems, our system, it's jarring, and we respond by resisting.
The author of Zen and the Art of Motorcycle Maintenance, Robert Piercy, he had a good quote actually. He said, we build up cultural patterns based on facts which are actually extremely selective. And when we have a new fact that comes in that doesn't fit our current pattern, we don't throw out the pattern, we throw out the fact. And he's saying that we have a biological immune system that will destroy a life-saving skin graft. But with the same vigor, fights any disease, pneumonia or whatever. Yeah. But at the same time, we have a cultural immune system that will fight off beneficial new ideas with the same vigor which attacks crime.
Yeah,
which is a good point. But so, why is this threatening? What does it change? Why is it even important that there's a fourth phase of water? Like, what does it change?
Well, we've grown up. Everybody grows up understanding that there are three phases of water, that there's solid, liquid, and vapor. When someone comes around and says there's a fourth phase of water, it tends to be jarring. I should qualify that. It tends to be jarring among scientists who deal with water and interfaces between materials and water. It's not so jarring for lay people who have great interest in water. Water now is perhaps the most important substance on the face of the earth, and many people are curious about water. People interested not only in science but even in spiritual aspects are certainly interested because water has a spiritual value in many belief systems, if not most belief systems, and perhaps even all belief systems. So there's an idea, for example, about information in water. Now, this is the idea that water can store information or data or such is anathema to most mainstream scientists, but there's a lot of evidence that actually water can store information. I organize scientific meetings. It's called the annual conference on the physics, chemistry, and biology of water. It takes place each year, and lately it's been in Bulgaria, where there are a lot of natural healing waters. And each year, multiple scientists come, and they demonstrate evidence, clear evidence, that water really does have the capacity to store information.
Well, one of the terms I've heard flying around in relation to your work is, so we have this easy water, and we have structured water, and this fourth phase, which is gel. Now, well, gel-like, plasma-like thing. So, what are these things exactly? What is structured water? How does it relate to easy water?
Yeah. Okay. Well, they're actually all different names for the same thing. So, the idea of structured water came many years ago because many scientists really did have evidence years ago that there could be water that has real structure to it. So, ordinary water, the perception among chemists and lay people is that the molecules are bouncing around randomly many times, billions of times per second, and so there's no organization to it, no real organization. In fact, even among scientists, there's no agreement on the actual structure of this kind of water. But long ago, people began to collect evidence that the water molecules could be organized in some way. And so the idea came to being of structured, so-called structured or ordered water. So I wrote a book in 2001, Cells, Gels, and the Engines of Life, and I talked about structured water. And then I guess we're responsible for some name changes. And the reason for the name change is we began to study this kind of structure, to learn more about it. And we found an experimental system where where we could create structured water, and this structure, as it grew from ordinary water molecules, it pushed out particles and molecules, it excluded them. So someone suggested, give it a name. So we called it the exclusion zone because it excluded. And the same person who suggested it said, well, it's a great name because exclusion zone, EZ, it's really easy to remember. And so the name stuck. It's an unfortunate name because this kind of water that's inside the exclusion zone has very interesting properties that go way beyond the fact that it simply excludes water. So gradually we discovered many of those properties. There are something like 8 or 9 or 10 features of this water that differ from ordinary water. And because these features differ so markedly from ordinary water, it looked like another phase of water. And this phase usually exists next to solids, or particularly solids that are water-loving, or so-called hydrophilic surfaces. That's the kind of water where you have a surface and you drop the water and it spreads out instead of beating up. Hydrophilic. So we've tried many hydrophilic surfaces, and very often these surfaces generate this kind of water. That is, they take ordinary water and they turn it into this easy or fourth phase water.
So why should anyone care about easy water? Why is it important for people? What's good about easy water?
Okay, good question. Why should they care? Well, first of all, your body is filled with easy water. Everybody knows that, or fourth phase water. Everybody knows that we're 2/3 water approximately. But the kind of water that is inside of our body is mostly not H2O, but fourth phase water.
Is this in general agreement? Everyone knows this, or is this something you've just found out recently and is yet to perpetrate through the kind of scientific community?
It's the latter. This is not widely known. However, it's widely known that water inside the cell is gel-like. That was established 60 or 70 years ago. Because, you can tell anybody who's taken a biology course and who's taken a cell and cut the cell in half, the water stays inside. It's not like a liquid water. It doesn't pour out as soon as you cut the cell. It stays. So it's gel-like. And as I said, this has been known for a long time. We found in our studies in the past 10 years that gels are full of easy fourth phase water. So, the logic is that if the inside of the cell is gel and gels contain fourth phase water, the water doesn't leak out of a gel. When you have gelatin dessert and you pick it up, the water doesn't dribble out, it stays inside. And it stays inside because the water itself is gel-like. I picked up gels in a Japanese laboratory from Osada sensei, who at the time was in Hokkaido, and I handled a gel, and it was just like gelatin dessert, except it was, instead of 95% water, it was 99.95% water, and it felt slightly wet, but basically just like gelatin dessert. And you asked the question, how could it be? This is essentially all water, right? But just a trace of solid substances, yet it all hangs together. So it hangs together because it's a gel. And the inside of the cell is just like a gel.
Okay, so we have some means of knowing that the human body has easy water in it.
Yes.
Again, why is easy water important? Why should people care about it? Okay, so we have it in our bodies, so what?
Because easy water surrounds every protein that's inside your cell. And every cell does work, and the work of the cell is done by the proteins. So for example, if you have a muscle cell, the muscle contracts. It's basically the proteins that do the contraction. They may undergo a change of shape from something like this to something like this, right? But every protein in healthy cells is surrounded by fourth phase water, easy water. That's the natural environment. And the protein can do this because it has the water around it. That's the normal milieu. If it doesn't have the water, if it's dehydrated, for example, it doesn't know what to do. It doesn't recognize it's a strange landscape. And so it either misfolds or doesn't fold at all, and your muscle is not working. So this water is intimately tied to good health. And it's important for us to make sure we have a good quantity of easy water. When you're born, your cell is full of it if you're normal and healthy. If your liver is not working properly, good chance it doesn't have its full complement of easy water.
So I saw this study saying that 75% of Americans are chronically dehydrated. So, you know, the obvious answer is just to drink more. But does it matter what kind of water you drink? Like, how do you? Okay, if they drink easy, rich water, what's the difference between that and drinking normal water?
Well, that's a really good question, and there are some hypotheses that are put forward, but it's not really clear until the evidence is in. And by the evidence, I mean it's necessary for somebody to compare the different waters and compare the effects on health in a double-blind study. Now, people have been manufacturing, creating various types of water, and they tout their water as being really good for health. And some of them say, oh yeah, this water contains easy water in it. There's reason to think that water that has a high fraction of easy water inside of it should be good for your health. And I can cite a reason for it, but I just want to say before I do that it's really important that somebody do studies to test these hypotheses. The reason I think it's good for you is that it basically refills what's missing from your cells. So if you drink easy water, you're replacing the easy water that's missing from your cells. And that brings us to juicing, taking green juices that many people do these days to improve their health. You're drinking, by taking the juice of these plants, what you're doing is you're taking the water from the inside of the cells of the plants. You're drinking plant cell water to replace basically your cell water. And it seems rather natural to replace what's inside your cell with something from other cells.
So what happens if you drink low easy water? Does your body stop having easy water inside it? I mean,
no, you create easy water. That's a good question. And the way you create it is the way we found you can create it inside the laboratory. It's created from light, the energy from light. And it's not necessarily visible light, although visible light does work. It's infrared light. And the question that so if you have infrared light coming to you, and it's received by your body then converts that water into easy water. That's what we found in the laboratory, and we presume the same inside the body. And so that's the reason why you go into a sauna, and it's hot inside, which means you're receiving a lot of infrared energy. And you walk in feeling rotten. You're feeling tired and depressed, and your muscles are aching, and you just want to go to sleep. And 20 minutes, wham, you're feeling marvelous after this. The aches have disappeared. Your headache is gone. You're feeling, instead of feeling depressed, you're feeling wonderful. And so, we tend to think of this as a purely psychological kind of effect. I think it's not. I think, of course, there's a measure of what's going on in your brain, but it's beyond that. I think it's at least the evidence that we've gotten from our laboratory is that it's the infrared energy that's coming, that's building the easy water and replacing the missing easy water in your cell.
Well, if this is happening and the body is automatically making easy water, then again, why do we need to care about this? Do we need to be? I mean, if your body's already making it, does it make any difference drinking like high quantity easy water? Does that help you?
It's a good question. It needs to be studied further, but it has to do perhaps with two things. One is the rate at which we can build easy water. So if you drink it to start with, then it's there already. It's not necessary to build it. And the second thing is, you mentioned chronic dehydration. I think when people begin to get gray hair, they become chronically dehydrated. And why is that? So how come people are born and they're 80% water by volume, and as we age we get down to perhaps 60% water by volume? And one of the reasons possibly is that you need to have to build this, you need a surface. Okay, and the surfaces inside the body are the protein surfaces mainly. And the protein surfaces have a particular organization on their surfaces of charges. If they don't have that, they can't build the easy water. As we get older, our surfaces deteriorate. The proteins that are made are not as youthful, shall we say, as the proteins that are made when we're in our infancy. We have mutations, and they can't build this water as easily as they could when we created proteins as children. And so we don't have as much easy water, so we're chronically dehydrated.
Okay, so have there been any studies or even anecdotal evidence to suggest that drinking high easy water is good for you? That it changes anything in the body?
Well, we have some evidence. We've begun studying this with limited funds that we have, and we're looking at plants, for example, and plant growth in the presence of easy water. And it appears that there's a positive effect of easy water. These are preliminary studies, and so we need to do a lot more. But this is exactly the kind of study that needs to be done. As I said, it's hypothesis at the moment with very little data. We need more evidence.
So the other thing from looking at your work that you were going into was this charge, negative electron charge, positive electron charge, and how that works in your cells and your body and in water. And you mentioned just very loosely the concept of free energy around this. Now that my ears peaked when you said that. And so could you just go into a little bit of detail? What kind of free energy? How do we get it? How viable is it as a means of free energy in the future?
Free energy. So we learn about, in chemistry class at the university, we learn about free energy. This is not the kind of free energy I'm talking about. I'm talking about energy that's free for the taking. It's literally free. So, and that gets back to what I said about infrared energy. So infrared energy is the energy that helps to build this water. It's so much more powerful than, say, visible light, infrared light. So when you think of infrared light, most of us think of a toaster or electric range. It glows red, and therefore it's generating infrared. Actually, infrared is being generated everywhere around us. It's free, literally free. And you can judge this yourself. If you turn off all the lights in the room, and if you happen to have a camera, an infrared camera, and turn it on, you get a beautiful image of everything in a darkened room. It's used by the military at night, for example, night camera. And what it means is that it's picking up the infrared light that's being generated by everything around us. And there's a lot of it. So it's free for the taking. It comes initially from the sun, and the walls have transduced the energy, and the walls and the table and this and your camera, they're all generating infrared energy. This is the energy that builds easy water. So in a sense, the energy comes free, and because the energy is all around, you have a lot of easy water in the environment. It's all around us. Anywhere in a river, for example, you have water that's flowing. The river will contain easy water. It builds around molecules. It builds around particles. The rivers are full of particles and molecules, and therefore they're full of easy water.
And then how do we turn that into powering a light bulb?
We can do it. We can do it because if we have a stationary system or a chamber, and we have the kind of solid that next to which easy water, a hydrophilic solid, easy water builds next to it, and so the easy water has negative charge, and the water beyond has all the protons that the water got rid of in order to build this negative charge. So effectively, what happens as this easy grows, it's negative, the region beyond is positive. So you stick two electrodes in, and you connect the electrodes to a light bulb, and you get electricity out of it. We've done it in the lab, and it works.
And how much electricity are we talking, and what kind of scale do we need in order to power cities and homes and things like that?
Well, it depends what you want to power. So we can, out of this, the laboratory version, we can get something like 1 milliwatt, and that's enough to light an LED, a light-emitting diode, is obviously not enough to power a home. We need hundreds of watts instead of milliwatts. So we're, of course, trying to perfect this system so that we can develop it into something practical. We don't know if we can, but we think we can. You can use you can have one small cell that generates a milliwatt, and you can put many of them lined up side by side, and you can therefore build. We know that we can do this. You can build to a larger scale. Practicality is the issue, but the beauty of it is that it's run by light, and the light is all around us, and it doesn't need to be sunlight. The infrared that builds this is around all the time, and it's water. It comes from something entirely renewable, so that makes it exciting.
So if someone out there who's listening to this wants to somehow get involved and they're interested in this and they think they may be able to work with you or help you, how do they find you? What is your website? What is it that you...
Oh, it's just if you Google under my name, I'm easy to find, and my email address is there all the time. I can give it to you right now if you like.
Well, what's the name of the organization that you're with that's doing this research, should I say?
Well, okay, I should make it. University of Washington is where I'm doing the research. We also have a company that we're developing that's independent of the University of Washington to try to bring to the world some of the outcome of this research. And it's not only getting energy from the environment, free energy basically, but it's also filtration, because this kind of water excludes most solutes, and the solutes can be pollutants that you want to get rid of. And it's a very simple system. It's a filter that has no physical filter. The filtration is done by the energy from the environment, which builds this fourth phase, or easy water, which excludes all of those nasty substances. See, so you just collect this water, and you have water that's free of these agents.
And so this organization or company that you made, it's called what, the Institute?
No, this is different. This is a company that we've just formed. It's called Fourth Phase. Okay, the Institute is a bit different. You're referring to something that's bigger than this. This is the Institute for Venture Science. And the Institute for Venture Science is a new venture that we've just put together. It certainly could include water, but it includes areas of science, every area of science that you can envision. The Institute for Venture Science. And our idea is to fund promising ideas that challenge current thinking, especially when current thinking seems to be obsolete or not working very well. This is a problem that exists in science today. If you ask yourself, how many fundamental discoveries can you name that have taken place during, say, the past 30 years? And by fundamental discoveries, I exclude technology. So, we have iPhones. This is wonderful, and we have the video camera that you're using to record this. Now, these are all technological developments that have had a lot of support from companies. We're talking about fundamental scientific discoveries. It's really hard to name something that's equivalent, let's say, to the discovery 60 years ago of the sequence of the structure of DNA, or 70 years ago to the splitting of the atom, or 90 years ago to the discovery of antibiotics, which led to the pharmaceutical industry. Fundamental, if you ask yourself how many you can name, most people can't name any of these that have actually come to fruition, not promises, but realized fundamental scientific revolutions. We'd like to change that. So we have a system to encourage fundamental breakthroughs. And the reason these haven't come, there's a lot of money for science these days, and despite the huge amount of money, there haven't been fundamental breakthroughs. 100 years ago, when there was almost no money, there were many breakthroughs, you see, so it's a bit of a paradox, and you ask yourself, well, what's going on here? Something is wrong. It doesn't make sense. And one of the reasons is the system, the bureaucratic system of funding of science. It's really difficult to come forth with a brand new idea and get the idea funded, because the idea threatens the people who are making judgment. The agencies, the funding agencies, like to choose the people who are most prominent in the field and to make judgment, because it looks good to the politicians that they've got the best scientists making judgment. But these people are the purveyors of the existing paradigm. They don't want to be threatened. And so scientists, and there are many who have really interesting ideas that challenge the existing paradigm, they keep them, largely, many of them keep them to themselves because they're fearful of this challenge.
And it's a problem. Everyone who's trying to push the boundaries of human knowledge encounters this
absolutely
resistance.
Yeah, it's not new, it's just that it's institutionalized.
So again, the Institution for Venture Science.
It's the Institute for Venture Science, ivs.org.
What kind of people would you look for to give you these new ideas, and how would you screen them?
We look for people who are creative and inventive. It doesn't matter if they have an academic position. That's not a criterion at all. We ask anybody out there who has an idea to present the idea. And we have a well-developed system to take care of the screening. The first is that we send it, so if we get a round earth idea, we send it to the flat earth people. And we know they're going to tear it apart. We understand that. And the proposer has a chance to rebut. And the people who make judgment are listening to both sides. They're listening to the proposer, and they're listening to the, you might say, the establishment people. And they don't care if the earth is round or the earth is flat. They just want to find the truth. These are people who are open-minded, seasoned, experienced, level-headed, selected carefully for their maturity and judgment. And so we're relying on those people to pick out the ones with the highest capacity to shake the earth, so to speak. And once we get one of these, or if we have the money, then we'll not only fund that group, but we'll look for other groups around the world, independent groups, who share this kind of vision, say that the earth is round, and we'll fund them as well. So then, next year, at the annual meeting of the Shape of the Earth Society, suddenly you've got a dozen groups coming who are reporting that the Earth is round. And, it's really easy to ignore one person who says the Earth is round, no matter what the evidence, by calling that person a crackpot. But when you've got a dozen different groups independently reporting the same shape of the Earth, each one using a different technique, it's really difficult to dismiss them all as crackpots. So what happens then is, within a short time, some traction, these people gain traction. And if they gain traction, it's really a kind of breakthrough, even a revolution, because then the world is thinking in a completely different way from the way it thought 2 or 3 years ago. So that's
what we need, for sure. I know that you have a new book coming out, and so far we've talked about water, but I'm very interested in what your new book contains. It would appear to me that the ideas in there are the very ideas that you're looking for in other budding scientists. Tell us a bit about your new work.
Well, yeah, okay. Maybe it's a bit premature because the book is not done yet. The first draft is almost done. But, I'm addressing some ideas in basic physics, ideas that we don't spend a lot of time thinking about. So, for example, one issue is what turns the Earth? Why do we have day and night? And I don't see many people researching this particular subject. The default explanation is that, well, the Earth has a lot of inertia and it was given a spin and it just keeps spinning. And it will take another X billion years for it to run down. I'm not so sure that's satisfying explanation. Most systems run down because of friction and such after time. And so I'm looking into other ideas, and the idea I might say is that the energy I think that spins the Earth has to do with solar energy, and how it does that is described in the book. I'm also interested, the book contains also ideas about gravitation. So most of us, we're sitting on a chair, and we never think about why we're glued to the chair. And of course, physicists understand that this has to do with the attraction of masses. But then if you ask the next question that a child might ask, well, why do masses attract? It's really difficult to come up with an explanation, especially an explanation that makes intuitive sense. And so another issue is the structure of the atom. Most of us, myself included, we presume that the structure of the atom is pretty much as we've seen for 5 generations now, starting with Niels Bohr and his solar system model, which has been modified many times. And simple questions arise that we don't think about, and I myself never thought about until the question was raised. For example, so the nucleus contains protons, and that's positive charge. So you might ask the question, if all that positive charge is crammed into the nucleus, how come the nucleus doesn't explode? And of course the physicists have addressed that, and the physicists invented a force, it's called the strong force, is a kind of glue that holds it together. Well, if there were evidence, independent evidence for the existence of a strong force, perhaps that would be satisfying, but to some people it seems like a patch to cover up a gaping wound, And if you take another step from there, ask a question, well, okay, so let's say this patch works and the nucleus stays together. Then you've got the electrons out there, and the electrons are negatively charged and the nucleus is positively charged, so how come the whole atom doesn't collapse?
Good
question.
Good question.
I think Niels Bohr was asked that question, and he just said, "Oh, it just doesn't," and I'm sure the answers are deeply embedded in the intricacies of quantum mechanics. But for the layperson, it doesn't feel intuitively satisfying that the atom itself seems unstable. It's about to explode, perhaps, and it's about to compress into nothingness. And so, and another issue is, okay, we have orbitals, and the electrons are in one and another, and how come they all repel each other? They want to spread out as much as possible. Why do they gather into these orbitals? And there are multiple questions that come from that. And so, in the book, I'm planning to address this, and I think that a satisfying model should at the very least be stable. Should hang together. It should not have a tendency to collapse or explode. And this is an important criterion. And so I've been thinking, and I've drafted a few chapters on an alternative model. And it's too much to explain. But actually, in essence, it's actually pretty simple. And so that's another aspect of the book. And how do birds fly? So questions like that. You look around, and if a child, a 13-year-old, a teenager asks, or a 6-year-old or a 7-year-old, how do birds fly? And your standard answer is, well, they flap their wings, right? But if you look up, you can see birds that fly without flapping their wings.
That's right.
So the default explanation is that there must be rising air. And there are many experiments that implicitly test that idea, or much logic that tests that idea and doesn't fit. And so there must be something else that's involved. It's sort of like a glider plane, no engine, but it stays up up to, I think the record is something like 10 hours or something. What's keeping it up? It wants to sink all the time, but something is keeping it up. And so you ask yourself, there must be something else besides flapping the wing. And I think there is, and the book addresses that question as well.
Excellent. These are excellent questions. Now the final question is the gigantic pink elephant in the room, which is consciousness, which is how we deal with all of this. How we understand it is through our consciousness. And the biggest single issue in all of the sciences is that not one model so far has come up with an explanation for the existence of consciousness itself. And the water question that I want to use with you here at the end to approach consciousness comes from the Russian film on water. And the story is of a shipwreck. And they get in the lifeboat and they're at sea for weeks and weeks and weeks with no water. And it was credibly reported when the ship sank, and it was credibly reported when the ship arrived in port many months later. And they were healthy, they were alive. And yet, the amount of water on that boat when they left the sinking ship should have lasted about maximum a week. So they were questioned and they were asked, how did you survive? And none of them wanted to say what happened. But after, this is according to the documentary, and I'm sure you've seen this part. Did you see it?
No, I haven't.
You didn't see that? Oh, well,
No,
this was in a Russian-made documentary about water.
Yeah,
One of the
I've
features.
seen some of them, but maybe not. Okay.
This story
Yeah,
was
yeah,
compelling
Yeah,
because it was so well recorded.
yeah.
And the captain was forced to tell them. And he said, we got so desperate, we were dying. And one of us came up with the idea of, let's imagine that the water around this boat is potable water and not seawater. What the hell, we're going to die anyway. And that's exactly what they did.
They drank seawater.
They drank what should be seawater around their boat, but it was potable, thus they survived several weeks. Okay, that story was reported by the Russians in a documentary. So it's not something was pulled out of a crackpot's hat. They were careful. So the obvious suggestion is that human beings in possession of self-aware consciousness were somehow able to transmute seawater into potable water. Now, is there anything in your research that would suggest how that might happen? And do you have any final comments about consciousness itself?
Well, I mean, you raise a topic with unending ramifications. So,
Exactly.
So the first thing that comes to mind as I was listening to you is that, you know, if there were somewhere in the presence of icebergs, when this has nothing to do with consciousness, but if the icebergs were melting, the melting ice is actually easy or fourth phase water. And it's possible that there was a sheet of this, the water tends to stick together, that there was a sheet of this on the water. It's been reported that ships that pass near icebergs slow down because the water is so viscous.
Ah, I see.
So you know, that's the first kind of default explanation.
Excellent.
Second thing that comes to mind is so-called quinton water, Quinton. It used to be that people would drink this kind of salt water that was taken from the ocean, and this was perfected by a French doctor, the name Quinton. And they used to drink small amounts of it, not huge amounts of it, and this water would make them healthy again. It was even reported that they would inject this into the blood, or even replace the blood. They did the experiment with animals, and the animals were able to survive with this. Then came antibiotics, and people stopped using it. But the factory is now in business again, and they're selling this to promote health. But you raised the question, for example, of transmutation, and I think what you meant by transmutation is a bit different from what I think of, but transmutation is actually something we think of alchemy when we think of transmutation, you know, converting lead into gold. But transmutation was an accepted science for a long time. Even Isaac Newton was deeply interested in this. And it was an accepted science until the time of Lavoisier, who declared that, oh, it can't be. And now it's a fringe science, if anything, and people are not permitted to study this because it's considered, well, it borders on alchemy. But I think a French scientist, Louis Kervran, found and wrote a book, maybe several books, in the 1950s or so, demonstrating that it seems to be a reality, not only in the case of being something being bombarded with high energy, but also in our bodies. And his book provided evidence that we are transmuting elements every day. So I don't know if it's true or not true, but if you read his book, it's really interesting because he brought back some of the old ideas with a modern twist to it, and he demonstrated that he spent a good part of his life studying disasters in France, and he couldn't make head or tail out of it until he realized that some of these disasters could be explained only if one element was being transmuted into another element. So I think this is ripe and open for discussion. I don't know if you mentioned transmutation, if that's what might have been going on, but I think what you're driving at is some kind of energy, some consciousness that could have an impact on the water. And I don't know if it's possible or not, but it's certainly possible that, and we're actually starting to study it ourselves, that intention and various kinds of energy could have an effect on the water. There's a lot of evidence for that presented at the meetings that we organize now in Bulgaria. And it's difficult to dismiss the evidence, even though many people would like to dismiss it. It appears that energy, including energy coming from us, can have a distinct impact on the water. So whether that explains what these people report or not, I can't say, but certainly it's interesting to speculate about such a possibility.
Well, let's hope that the Institute for Venture Science gets the kind of people who will grapple with these core ideas.
Oh, yeah.
Because they're not crazy ideas. You've just said there's a lot of evidence that intention does affect water. And intention, of course, is conscious. So I look forward to your finding some amazing individuals who get the funding, who do the research, who get it duplicated at various places around the world, who bring it to the attention of people who need it right now, especially with so much water shortages and water problems and water pollution around the world. It's enormous, and the large corporations buying up water rights all over the world, including in Bolivia, where I think the first group of people on earth actually went up against the big corporations and said, "You're not buying our water. It is our right." And that happened because the president of Bolivia is a native, he's an Aboriginal, right? So there is an awareness, and your research in water is bound to be needed in my mind. And so for those listening to this interview, check out the Institute for Venture Science. And thank you very much. That was a lot of time you shared with us. And,
thank you.